All right. Good afternoon. I posted the study guide for the exam, for our first exam. So please take a look. If you have any question, or if you want me to work on any specific problem, you can ask me after the break of the class. I also posted new homework, which is due on March 20, 2 weeks from now. 21st. So, any question before we start? All right, today we are going to start chapter 4. This chapter has two parts. First part is talking about deflection. And the beam. And second part is talking about the buckling. So today we are going to talk about deflection of the beam when it's under loading. We would like to see if a beam like this or like this, it's under external load F1, some distributed load and concentrated load at W. What would be the deflection of this beam? If I represent deflection by y, how the y, if this is x-axis, how the y is varying over the beam. So y as a function of x. At each specific location of the beam, what would be the y? So this is for the first part. Before I start deflection on the beam, there is a small topic that I would like to cover. Spring is a mechanical component where if you make any deflection on that, it's going to exert the force in the opposite direction of the deflection. So if this spring is at free length or free position, and you make some deflection on that, delta L, you make this deflection, you are going to feel some force applied upward on your finger if you make this deflection. So this force is due to this deflection. So this is how the spring is working. So you make deflection, the force is going to apply to this deflection. So there is a relation between the force and the deflection. You can connect these two by this coefficient that we call a spring rate or a spring constant. So if I draw the force versus the deflection, you are going to get a linear function which represents this one. And this coefficient is called the spring rate or spring constant. So for other mechanical components, whatever is connecting force to deflection, whatever is connecting force to deflection I labeled with the coefficient of A. That coefficient is called spring rate. So for other mechanical components, for example, we have a rigid bar which is under axial loading of F. So due to this load, we are gonna see deflection. If this is L, if the length of bar is L, due to this force, we are gonna have some elongation on the bar, and it's gonna make it like this with the elongation of delta L. If I ask you to write the equation for a strain, you can say delta L over L, whatever is the elongation divided by the length of the bar. And if I ask you to write the stress applied to this, if this cross section is has the A as a area, it's going to be force divided by A. So stress, strain. And we know that the sigma would be the modular elasticity times strain. 1, 2, 3. So sigma would be F divided by A, and strain is delta L divided by L. Now I make this equation something look like this. I keep force one side and move A to the other side, A times E. A times E divided by L multiplied by delta L.
What does the large E stand for?
Large L?
Large E.
Modular elasticity. This is the correlation, the relation between stress and strain. Sigma equals to E times strain. It depends on the material, so you can read it from the table depending on the type of the metal. So now this equation is gonna show me the relation, the correlation between the force that we apply and elongation that we get. So if you compare this coefficient connects force to elongation. So the stiffness or spring constant for a rigid bar, which is under axial loading, is gonna look like AE divided by F. That's
So you've got F equals A delta L, and then F equals K delta L.
I was saying that whatever is connecting force to deflection is gonna cause the spring rate.
Okay.
So this is gonna be, I mean, let me write it K
Okay.
just to make
That
it,
was what I was just thinking.
just to represent the coefficient.
Thank you.
Yep. So it can be, this logic can be applied for any other component like this beam, which is under a force applied at the middle of beam. Due to this loading, it's gonna make deflection. So it's gonna look like this. Where y is representing the deflection. So now, if you can find the correlation between this F and deflection at the middle of the beam, F and Y, then whatever is connecting these two is called a spring rate for the beam, which is under a loading, which makes the deflection. So this can be applied for other mechanical components like beam. So by knowing this, we can start this topic, deflection and the beam. Suppose we have a beam which is under distributed load of W. So I can ask you to shear force diagram and bending moment diagram. So for shear force diagram, it's gonna look like this. For bending moment diagram, it's gonna look like this. You know how to do that. So this is the shear force, this is the bending moment. There is a relation between shear force Q or W, which is load density, we covered these things on chapter 3 when we were talking about shear force, bending moment, and the load density. If we have any load density, these two equations are valid. So these are coming from chapter 3. So due to this loading or any other different types of the loading, we are going to have some deflection. If this is y-axis, this is x-axis. So deflection is represented by y. Y is deflection. So the beam is gonna look like this. So we can prove that at each point of the beam, suppose this point, it's kind of curvature here. So each point has its own radius of the curvature. So this point has the radius of curvature with this length. This point has the radius of the curvature with this length. This point has something like this. So each point has its own radius of the curvature that I represent by rho. It's a mathematical thing which shows the radius of curvature at each point. For example, for circle, radius of the curvature at any point is gonna be r. So this is gonna be rho equals to r. So we can prove that 1 over rho at any point is gonna be the bending moment applied to that point divided by modular plasticity times second moment of area for the cross section. One over rho is gonna be m over EI. So at any point, if I ask you find the radius of the curvature, you should find the bending moment. Bending moment is coming from this graph, divided by E, modular elasticity of the material. I is the second moment of area for cross section. If it's circular, it's going to be pi d over 4 divided by 64. So if it's rectangular, it should be about the z-axis, because the rotation is about z-axis. Anyway, we have this equation. There is a mathematical process that I have on the slides. I would like to show you, but model. But anyway, I can prove easily that 1 over rho this equation m over ai it's gonna be the second derivative of y with respect to x. Second derivative of y with respect to x. It's not a difficult proof, but since the equation is long to write on the board, I just skip the proof, and you don't need to be worried about that. But we can prove that mass bending moment divided by the EI is going to be the second derivative of y, which is the deflection with respect to x. I can ask you this: what is going to represent dy del y over del x? Del y over del x. The answer is the slope at each point of the beam. If I ask you to find the slope at each point of the beam, dy over dx is going to represent that. So ds second derivative of y with respect to x is going to be equals to m over ei. Now, if I differentiate bending moment with respect to x, I can get the shear force. So if I differentiate this, m would be ei. This shear force would be, if I differentiate this, I will get the third order derivative to get v. And if I want to get q, I should differentiate v, which is going to give me the fourth order. The fourth order of derivative with respect to x is going to give me the load density. So for this given problem, I know that the Q is equals to negative W. The load density is going downward, so it should be negative W. So Q is going to be negative W. So Q would be, which is negative W would be dV over dx. I'm going to start from this. If I want to find this equation, which is the shear force, I can say V would be the integration of negative W times dx. The integration of that is going to be negative Wx plus C1. C1 is constant. How can I find C at x equals to 0 at the starting point of the beam? The shear force should be W times L divided by 2. This is WL divided by 2. So V should be WL divided by 2. If you plug in x equals to 0, V would be negative W times 0 plus C1 equals to WL divided by 2. So C1 would be WL divided by 2. So this equation is going to look like this. So shear force is going to look like this. I mean, you can get this equation, this line, by the approach that we covered on chapter 3. Just cut the beam and write the equilibrium equation to find the shear force. This is another way that you can drive the shear force. Now I'm going to get the bending moment by using this equation. V, which is this, dm over dx, then m would be the integration of v dx. V is here. Derivative of this is going to be negative wx squared divided by 2 plus wlx plus c2. Derivative of negative wx is going to be negative wx squared divided by 2. wl divided by 2 is constant. I should have x, and c2 is constant. What would be the boundary condition at x equals to 0 or x equals to I forgot this. At x equals to 0 or x equals to L, we know that bending moment should be 0. If you plug in x equals to 0, 0, 0, C2 should be equals to 0. So M is going to be so I could find bending moment as a function of x, which is going to represent this figure. My goal is find y deflection as a function of x. Y as a function of x. So now I have m as a function of x, which is equals to second derivative of y with respect to x. If I integrate this twice, I will end up to y as a function of x. And this is what I'm going to do. EI, second derivative of y with respect to x is going to be m. If I do the integration of m dx is going to be AI, first derivative of y with respect to x. Integration of m. Just put the integration here. It's x squared is going to change to x power 3 plus WL x squared divided by 2 times these two, 4 plus C3. This is EI times the slope. This is the slope. Slope of the beam is gonna look like this. If I integrate this one more time, I will get one. If I integrate m twice, or integrate this one more time, I will get EI times y. Integration of this negative WX4 divided by 24 plus WLX3 divided by 3 times 4, 12 plus C3 times X plus C4. So this is EI times deflection. And I have two coefficients of C3 and C4. So I need two boundary conditions. If you look at the beam, at a starting point at x equals to 0, y is 0. We don't have any deflection. Just plug in x equals to 0. This term is gone, this term is gone, this term is gone. So C4 y C4 is going to be 0. It should be to satisfy the first boundary condition. Also at the ending point, y is equals to 0. At end of the beam, we don't have any deflection. So just plug in x equals to L. I will get EI times 0 equals to negative WL4 divided by 24 plus WL4 divided by 12 plus C3 times L equals to 0. If I do math, I can cancel out one of the L. C3 would be negative WL power 3 divided by 24. Let me write the equation right here. Now I can write y as a function of right hand side. Y would be 1 over EI times negative W x4 divided by 24 plus WL x3 divided by 12 plus C3 is negative WL3 over 24 times x. Or each term has W, so I can take them out. Each term I can take 1x, and I can take this 24. So I will get Wx divided by 24 EI multiplied by, what is left here, negative x3 divided, not divided, plus Lx2, 2Lx2, and negative L power 2. Now, at any specific point of this beam, whatever is the x, L over 2, or any other point, if you plug in x here, you can find y. This is the deflection. If I ask you to find the slope dy over dx, here we calculated dl over dx, or you can differentiate this with respect to x to find the slope. And if I ask you at which point of the beam we are going to have the maximum deflection, for this type of the loading, it's obvious that the maximum is going to occur at the midpoint. So at x equals to L over 2, just plug in x over L over 2. My max negative 5 omega L over 4 divided by 384 EI. Just I plug in the x equals to as always.
Yeah. And this is just for these programs.
It's just for the beam which is under this type of the loading. For any different loading, what you need to do, you need to find M. If I gave you another type of the beam, what you need to do, you need to find bending moment diagram. Basically, you need to find this equation. After you find the bending moment equation, then you can start from here, from this equation. The first integration is going to give you the slope. Second integration is going to give you y. So, on the back of the book, table A7, A9, sorry. Table A9. Table A9 has provided some standard configuration. For example, you can find this pin with the loading of W as a distributed load with the length of L, and you can find a Y by this function, so you can find on table A9. If you look at that, if one force at the distance of A and the length of L has been applied to this cantilever beam, what would be the Y? You can find the Y from the table A9. So there are some standard configuration there that you can look at those functions if you don't want to derive. So, but I can ask you, if I want, I can ask you to derive the deflection function for this loading and this beam. You should just do the same approach that we did by driving the bending moment, then do the integration twice. So, let me solve one example. And explain superposition method to find the deflection on the beam. Suppose you are given with a beam like this. W, simply supported beam. The length of the beam is L, and one force at the this is point A, point C. One force at point B with the magnitude of the F and distance of A is applied to the beam. So we have two loads, one distributed and one concentrated load at the distance of A. We were asked to find deflection function on the beam. So y, how the y is varying with x. There are two ways that you can solve this problem. First approach. Find bending moment function. Find this function. You know how to find bending moment diagram. And after you find bending moment equation, differentiate it, integrate twice, you will find y. So it's a long approach. I mean, if you want to do that, you can. But second approach is apply superposition. Just break this beam to two beams. One beam with distributed load plus one beam with concentrated load. Table A9. Table A9. It has the equation for this type of the beam, the length of L, distributed load of W, and also table A9 has a cantilever beam with the length of L, where force F is applied at the distance of A. What would be the deflection? So you will find Y1 from here, Y2 from there, and add them up by applying the superposition. So the idea is simple. Just what you need to do is look at the table A9. For this one, it's going to be WX24EI negative X. For this, it's going to be I'm looking at table A9. So for section AB from this section, Y is going to be YAB is going to be force Bx divided by 6EI x power 3 plus B squared minus L squared. So if you are looking for deflection for section AB, any x between A and B, you should use this equation, minus. And for section BC, is going to be F times the distance of A, L minus X divided by 6EI. AB and BC. Now, if you are looking for the total deflection for section AB, add Y1 plus YAB, add these two. For section BC, add Y1 plus YBC, X between B and C, X between A and B. So again, if you don't like superposition method, which is a much easier method, you can start from scratch, find the bending moment diagram, find M as a function of X, integrate twice to find Y as a function of X. How can we find the maximum deflection location on that problem? If I ask you at this point of the beam, we are going to have maximum deflection, how can I find that for this one? Say it again.
For YAB, YBC, there's 6 is on the bottom, right?
Yes, 6 times EI. the question is where on the beam we are gonna have the maximum,
Take the derivative and set it equal to 0.
take the derivative. I'm looking for the maximum value for this function. So take the derivative of this, set it equals to 0. Take the derivative of this, set it equals to 0. And find the value corresponding to that x and compare which one is the greatest. So that x is gonna be the greatest deflection. Or you can plot, if you want, you can plot this function and this function and see that you will have the maximum deflection. All right. I'll stop here. So we continue after the break. I will collect the homework.